Good afternoon, ladies and gentlemen. Welcome. My name is Moni Lustig, and I am the CEO of DNA Labs. It's my pleasure to welcome all of you to our first webinar, The Benefits of Pharmacogenomics. Thank you all for taking the time out of your busy day to join us today. It's unfortunate that we are doing this over Zoom, and I hope to be back demonstrating our products in person to all of you in the not-too-distant future. DNA Labs Canada is a Toronto-based genetic testing company. Our current product offering includes three main classes of tests. Our pharmacogenomic test, which is a subject of today's webinar, Match My Meds, our lifestyle genetic test, Love My Health, and our cannabis sensitivity test, Test My Tolerance. We're here today to hear from our expert panel about pharmacogenomics and its applications. I would like to now introduce our panel. Iris Kohn graduated from Pharmacy School of the Heinrich Heine University in Germany in 1995 and is a registered pharmacist in Germany, the USA, and Canada. Iris served as a clinical pharmacist in Germany from 1996 to 1998 and in various hospital settings in the United States, in Iowa City and Baltimore from 1999 to 2012. During her time at Johns Hopkins, she directed and supervised projects and initiatives that have not only increased patient and medication safety, but have also utilized and implemented novel technology utilized by healthcare providers that improved the daily care of patients. Iris joined the Hospital for Sick Children in Toronto in October 2013 as a clinical research pharmacogenomic advisor in the Division of Clinical Pharmacology and Toxicology. Since her arrival, she successfully developed the clinical pharmacogenomics testing program and helped create a pharmacogenomic clinic. Her research focuses designing a future pharmacogenomics service, including different technology platforms and advancing pharmacogenomics testing into therapeutic management of daily clinical care. Next is Dr. Tim Cook, who is the current Chief Medical Officer of a new clinic that opened up in downtown Toronto called Regen Scientific. Dr. Cook completed his MD at Queen's University in 1986, in General Internal Medicine, Fellowship at University of Toronto in 1995, and Master's degree in Public Health from University of London in the UK in 2006. Retired Lieutenant Colonel Cook enjoyed 20 years in the Canadian Armed Forces Medical Services, retiring in 2003. He trained in occupational and environmental health, had several deployments abroad, and also served as a personal physician to two Governor General of Canada. Since then, he has been recognized for his work in executive and corporate health and was the Associate Medical Director and Chief Medical Officer at two executive health clinics in downtown. Over the past decade, Dr. Cook has expanded his interest in disease prevention and management through the incorporation into his life and clinical practice of mind, body, and medicine, mindfulness mediation, and integrative health. 2013, he founded the P3 Health Clinic for personalized participatory preventative medicine and directs a multidisciplinary team of conventional complementary health practitioners. Now, as of about 2-3 weeks ago, he is now the new Chief Medical Officer at Regen Scientific. Next is our Dr. Aaron Goldman. Dr. Goldman is the Chief Science Officer of DNA Labs. Dr. Goldman oversees all aspects of genetic test design, interpretation, and implementation. Prior to his work at DNA Labs, Dr. Goldman was the Director of Genomic Services at the University Health Network's Clinical Genomics Center, and also served as Research Program Director and co-founder of Mount Sinai Hospital's Office of Personalized Genomics and Innovative Medicine, which was established to translate genomic discoveries into routine medical practice. Dr. Goldman earned his PhD in molecular genetics from Yale University and postdoctoral studies at the University of Toronto. I would like now to ask Aaron Goldman to start our webinar.
Thanks, Moni. Thanks everyone for joining. Let me share my screen here. All right. So thanks, everyone. Looking forward to presenting here and to hear the panel discussion afterwards. So I'm going to provide some background information, really, what is DNA, what is pharmacogenetics, why we need it, that sort of thing. And then I think Iris and Tim will talk about how they use pharmacogenetics in their practice. So the first topic is, what is DNA? So I'm sure everyone here has heard of DNA. Some people might know exactly what it is, but basically it's a long string-like molecule that's found in almost every cell in our body. And it forms a code, and the code is made up of these letters or these nucleotides, which are represented by these letters, the letters A, T, C, and G. So you might have seen that in the media, this code. And it's a very long string a long string molecule. And if you actually take all it's so long that if you take all the DNA in one single cell, one microscopic cell in our body, and stretch it out end to end, it will actually be about 2 meters long. And if you take all the DNA in your body and stretch it out end to end, it'll actually wrap around the solar system twice. So it's a massive amount of DNA that we're walking around with. And because it's a code, it's actually a massive amount of information. And it's one of the more amazing things our body does, is actually package all this DNA into each of our cells. And it's not just crumpling it up and throwing in there, it's actually very organized, the way it's wrapped around different proteins and formed into these chromosome structures. Because every time the cell divides, it has to copy the DNA. Every time a gene is turned on or off, the DNA has to be accessed. So it's a pretty amazing thing that our bodies do. So as I mentioned, it's a code, and it's made up of these letters. There's actually 3 billion letters in our genome. So we're walking around with 3 billion letters. And actually we have 2 copies of our genome, one from mom and one from dad. So we actually have 6 billion letters in each of our cells. So it's a massive amount of information. And scientists have figured out how to read this information. So the information is organized into sections, which are called genes. Each gene, and this is very overly simplified, but each gene is the instructions or the blueprint that tells your body how to make a certain protein. And the proteins are really what does everything in the body. And scientists have figured out how to translate the gene information into a protein. And we use this code here, this genetic code wheel. And the way it works is every 3 letters of the DNA encodes 1 subunit of the protein, which is an amino acid. So we have machinery in our cells that jump onto the DNA. It's actually RNA. We're skipping a big step here, but they look at the first 3 letters, A, T, G. And if you look at the genetic code here and you read it from the inside out, so A, T, G, that encodes a methionine. So our machinery in our cells read the ATG, pulls a methionine out of the milieu of the cells, and that forms the start of the protein. Then the machinery moves on to the next 3, ACG, again, going back to the code, ACG, so that's threonine. Again, it pulls the threonine out of the cytoplasm and starts building the protein. Now, and then it reads along the entire gene and builds this protein. Now, again, this is overly simplified. Not many proteins are this short, but what the protein does then is it folds up into a 3-dimensional structure, and this is what does everything in our body. So it could be a structural protein that holds cells together. It could be a protein that turns genes on and off. It could be a protein that metabolizes nutrients or caffeine, that sort of thing. And for the purpose of this talk, we're talking about pharmacogenetics or drug compatibility. So in this case, the enzymes that we're talking about metabolize medications. Now, humans are about 99.9% the same, which means we're 0.1% different. And 0.1% doesn't sound like a lot, but when you're talking about 6 billion letters, that translates into about 60 million differences. So we're all walking around with these differences. Now, the most commonly studied difference is a single change of a letter. So if you look at this C, T, T that's in the middle here, and imagine that for this T, 70% of the population have a T there, but let's say 30% of the population have a C in that same location. So you can see how that single change which is called a single nucleotide polymorphism. So these are nucleotides. So that single nucleotide polymorphism actually does change the protein. So a lot of SNPs don't have any impact on the function of the protein. Some SNPs can make the protein work faster, some SNPs can make the protein work slower. So that's basically what we're looking at here. Another type of genetic variation I'll just quickly mention is a copy number variation. So I mentioned we have 2 copies of every gene, one from mom, one from dad, but there are actually exceptions to every rule, and there are some genes, and relevant to pharmacogenetics, there's a gene called CYP2D6, which is commonly found to be duplicated. So instead of the normal 2 copies, you might have 3 copies or 4 copies of the gene, which would mean that you have increased enzyme activity or potentially too much enzyme activity. So we'll touch on that later. So now we have technologies that can read DNA, and we understand what it does. And there's actually a bunch of different types of genetic tests out there. We're going to be talking about pharmacogenetics, which is really about drug compatibility. As Moni mentioned in the introduction, DNA Labs also does nutrigenomics. So this is looking at nutrition and lifestyle, looking at potential food sensitivities or nutrient deficiencies, that sort of thing. There's also companies out there that do consumer genomics. These are companies like 23andMe or Ancestry.com. They're the most commonly known type of genetic test, and that's really for understanding where you came from and potentially to find long-lost relatives. And another type of genetic testing is looking at inherited disease risk. And this is where, looking at risk for certain cancers, certain cardiac or cardiovascular disease, that sort of thing. This can oftentimes be a little bit more complicated and requires genetic counselors, medical geneticists to help decipher the information and deliver that to a patient. And importantly, pharmacogenetics is not disease risk. So when you're talking about a pharmacogenetics report, there's no scary information. It's really looking at whether the drugs are going to work for you or not. We're not going to tell you, like in this type of genetic test, the inherited disease risk, we're not going to tell you have a Huntington's gene and you're going to have the disease. So there's no scary information. So I just wanted to highlight that key difference. So why do we need pharmacogenetics? So the short answer is that drugs just don't work the way they should. Current prescribing practices cause adverse drug reactions or unwanted side effects at an alarming rate. In Canada, adverse drug reactions kill more than 10,000 Canadians every year. In Canada, there's about 200,000 severe adverse drug reactions reported every year, costing the healthcare system billions of dollars. Now, of course, that's reported. There's a lot of adverse drug reactions that go unreported, so that number is probably a lot higher than that. And adverse drug reactions is actually the 4th leading cause of death and illness in the developed world, which is crazy to me. So we can be doing a lot better with our drugs. Next couple of slides, I'm going to show some data from a few different studies. So this came out of a meta-analysis that looked at about 3,000 different treatments from a bunch of different clinical trials. And amazingly, half of the time, it's unknown whether the drug is effective or not. It's only beneficial about a third of the time, and another third of the time or so, a quarter of the time, it's unlikely to be beneficial or even likely to be harmful. Here's another figure showing that for some commonly prescribed drugs, efficacy rates are shockingly low. So this dotted line here in the middle is the 50% efficacy rate. And you can see for most drugs, you're lucky if it works more than 50% of the time. Another study showed that for patients with OCD, obsessive compulsive disorder, doctors had to try an average of 4.2 times with different drugs and dosages in order to get it right. So we could be doing a lot better. Similarly, this is from another study from looking at patients with major depression. The first drug doesn't work about 67% of the time. And then the second drug actually doesn't work about 75% of the time. And I wanted to show this slide here because not only shows that the drug doesn't work, but there's also a time component to this. So when you take an antidepressant, you have to give it at least 4 weeks to kick in to see if it actually works. If it doesn't work, you can't just stop that drug and start another one. You have to do this extended washout period in between drugs, which typically takes 2 weeks to a month or longer sometimes. And then when you do another drug, again, it's another 4 weeks. So here, in this case, you're looking at minimum 3 months. You've tried 2 drugs and it still doesn't work. So we can be doing a lot better. So I think pharmacogenetics can really help in this, address this issue. So various factors do play into the effect of medication, like gender, age, weight, comorbidities of other diseases, what other drugs you're taking. But genetic factors are arguably the most important piece of information that's not being considered when making prescribing decisions. And they account for up to 95% of drug response variability. So before I move on, so I think today we're talking about pharmacogenetics. I think 5 years from now, we're going to look back at 2021 and wonder how we practiced medicine without it. As we do, like, you can't imagine practicing medicine without some of these other tools like the stethoscope, blood pressure cuff, and so on. So why now? Why are we talking about pharmacogenetics now, and why hasn't this been fully implemented? And it really comes down to technology development and cost. So this is a very famous figure from my field of genomics that really looks at how the cost of obtaining a human genome, the cost of sequencing a genome, has changed over time. And the first human genome to ever be sequenced cost about $3 billion. That was the Human Genome Project, which took about a decade, a bit longer than that. And some of the technologies that were developed during the Human Genome Project has really led to an explosion of knowledge. So DNA sequencing technology was largely following the trajectory of Moore's Law. If you're unaware, Moore's Law basically states that computers get twice as good and half as expensive every year. So it was largely following that trajectory until about 2007, when something called next generation sequencing was invented. And this is really like going from a typewriter to a computer in genetic sequencing technology. And that's really driven the cost down from about $100 million only 20 years ago down to about, we're actually at about $1,000 now for a genome, which has just been incredible. And what this has enabled is a massive amount of clinical research that has dramatically increased our knowledge about how DNA works. So we know a lot more about DNA now because of this technology. All right, so let's now get into pharmacogenetics. So this is an area under the curve graph, which some of the pharmacists out there might be familiar with. And what you hope to happen, and the way medicine is currently practiced, is everyone gets the same first-line treatment, the same drug and dose. And what you hope to happen is the drug concentration increases in your blood. It gets to this therapeutic window, so it starts to work. And then your body metabolizes it out and it's cleared out of your body. Now, of course, if you're taking many doses over multiple days, you want to keep the levels within this therapeutic window. Now, that's unfortunately not how it works in practice. Everyone metabolizes drugs at different rates. So you might have some people that are ultra rapid metabolizers. So they metabolize the drug so quickly that it's cleared out of their body before it has a chance to accumulate to therapeutic levels, so it just doesn't work. Or conversely, you might have people that are poor metabolizers, or they metabolize the drug too slowly, that it builds up in their system, especially if they're taking multiple doses over several days. It builds up until it gets to toxic levels, and that's when you can have an adverse drug reaction. So pharmacogenetics looks at these drug metabolizing enzymes, and we can use that genetic information to better understand the patient and guide them, as some people might need lower doses, some people might need higher doses or alternative medications, so that everyone gets the right drug in the right dose. And this is an area of medicine called personalized medicine. And I've been saying for a few years now that pharmacogenetics is sort of the low-hanging fruit of personalized medicine. And that's because of a number of reasons. One, the genes that encode the enzymes that metabolize drugs are very well characterized. We know a lot about the genes and a lot about the variant, the SNPs and other genetic variants that influence their activity. The cost to genotype has come down. And we only have to genotype a few genes. We don't have to sequence an entire genome. So the cost has come down to the point where it's now more accessible. And evidence. So there's tons of evidence out there, and there's actually clinical guidelines available that tell you basically if you have a certain gene, this is how you should change the prescription. And I'll give you some examples of that now. So there are a couple consortia out there. The most well-known one is called the Clinical Pharmacogenetics Implementation Consortium. This is a group of about 100 different academic medical institutions around the world. And it's basically a group of multidisciplinary practitioners, medical geneticists, physicians, pharmacists, pharmacologists, and so on. And they look at every clinical research study that analyzes a certain gene-drug interaction, and they publish guidelines. One very good resource that's on the web is called the Pharmacogenomics Knowledge Base, or PharmGKB. On this website, they actually annotate all the guidelines that's published by CPIC, but also by other groups such as the Dutch Pharmacogenetics Working Group, the Canadian Pharmacogenetics Network for Drug Safety, and also oftentimes drugs that have had their labels updated recently, or new drugs that come on the market, they oftentimes have pharmacogenetic information right within the drug label. So this database really curates all of that information in one spot. So it's a great resource. The other thing they do, which is very important, is they rank evidence based on the level, or rank genetic associations to drug metabolism based on levels of evidence. The reason I'm showing this slide is that just so people understand the difference, sometimes there are drugs that have very high levels of evidence, where there's to the point where there's actually guidelines available. But then there's also gene-drug associations that have some evidence out there, but it's really low or even unsupported. So those are like the level 3, level 4 drugs. And when you're comparing different pharmacogenetics companies, having more drugs on the panel is not necessarily a good thing. I've seen a lot of companies that provide recommendations based on these level 3 and level 4 those levels of evidence. And I think that can be very dangerous, because the last thing you want to do is tell a doctor to prescribe something they might not be comfortable prescribing when there's no evidence behind it. So I'll spend the next just a few minutes going through some examples. So here's an example of one of the guidelines that's published by CPIC, looking at SSRIs. These are antidepressant selective serotonin reuptake inhibitors. Right within the guidelines, there are tables. So here's an example from the sertraline table. So sertraline is Zoloft, commonly prescribed antidepressants. And right within the table, it shows you that for people that are poor metabolizers, the implication is that they'll have lower metabolism and therefore higher levels of the drug and potentially higher risk of side effects. And therefore the recommendation is right within the paper saying that you should consider a reduction of dose. And going back to these tables, how that works is a poor metabolizer, they won't clear it out very quickly. So it builds up into their system to toxic levels. Recognizing that they have a risk of that, you can provide a lower dose to make sure that that the drug works properly for them. Another example is Plavix. This has sort of become the poster child for personalized medicine because it's a blood thinner that's used, after anyone has a heart attack, they get a stent put in and they're put on Plavix. This is a drug that is not metabolized well in a huge portion of the population. So 30 to 40% of the population can't metabolize this drug. So it's almost like, the analogy I like to use is it's almost like you think your seatbelt's on, but it's not on. So here, for example, poor metabolizers should really select an alternative drug. And sometimes the guidelines actually provide alternatives, which can be very helpful. Another example, this one comes from the Dutch Pharmacogenetics Working Group for Nexium, which is a very commonly prescribed proton pump inhibitor, PPI. Right within the paper, it shows you that ultra-rapid metabolizers, so people that metabolize the drug too quickly, should have an increased dosage. That's showing this on a table. Again, they need an increased dose because they clear it out so fast that it never accumulates. So if you give them a higher dose, they can get relief. And the last one I want to show is just an example from a drug label. So here's the drug label for Celebrex, commonly prescribed pain medication. Right within the drug label, it says that poor metabolizers should consider starting the treatment at half the lower recommended dose. And that's for the same reason as I showed before, because they won't clear it out of their system quickly enough. So I think that's a quick introduction. I'll now pass it off to, I think Tim's going to now talk about how he uses it in his practice. Thanks.
Thank you, Aaron. That was terrific. Good to go back to first principles. I would just like to spend a few minutes discussing how these data can be used kind of at the coalface of clinical medicine and how it's impacted my practice. I recall when I was working at MedCan in the executive health world back in 2005, we had our very first access to a genomic testing, and it was about $5,000 at that time. And I will say that the amount of information that was in there was remarkably little, but it was still useful. Nowadays, we can access probably 10 or 15 times that amount of information for 1/10 the cost. Unfortunately, it's still not apparently cheap enough for the Ministry of Health of most provinces to have supported it, except in some very specific circumstances. And I will say that the pharmacogenomics implication for patients can be quite remarkable because, as Aaron mentioned, there are many hundreds, in the order of 400 or 500 medications now that have pharmacogenomic implications. And these are relatively commonly used. And I will say one of the most prolific uses of medications in the world are antidepressants. And in my own experience, it's the trial and error approach is fraught with challenges because they take often 6 or 8 weeks to work. And so it takes you that long to figure out if they're either ineffective or going to cause side effects. And so if the average number of medications required, even by psychiatrists, to get to a medication that actually works without adverse effects is 4.5, then you're looking at almost a year of messing around potentially for any individual patient to get to an antidepressant that's actually useful. So, I had a case literally about 2 months ago of a young woman who was in her late 20s that had suffered from anxiety and depression for most of her life. Her psychiatrist had settled on Celexa as the medication that seemed to be effective for her. But when she saw me for her kind of an executive medical, she said, the reality was she was really not feeling that it was very effective. And he'd run it up to the maximum dose. And so I said, well, you haven't done your pharmacogenomics. Why don't we do that and see what that might inform us about your response to these medications? And sure enough, the results back from the DNA Labs pharmacogenomics suggested that Celexa was not going to work. And the joy of this particular report, which is I will just say that the bioinformatics and the presentation of data in the genomic world is critically important for the user interface. And so I really appreciate the DNA Labs report, which kind of has a stoplight approach. Green is you're good to go. Typically, a response at the usual dosing is expected without adverse effects. Yellow is potentially dose change, but you could use that medication. Red is don't use that medication at all. Try a different one because it's either going to be ineffective or have adverse effects that would be intolerable. And sure enough, Celexa was on the red list. So, well, you're not on the right medication. The green one, and there was only a couple out of there's a laundry list of antidepressants that have pharmacogenomic implication. And the one that looked like it was the green was Wellbutrin. So I switched her from Celexa to Wellbutrin, and literally 6 weeks later, she's saying, wow, she's not felt this good. Her anxiety and her depression are, the best they'd been in literally a decade. So I do think that for a nominal investment, this particular approach to medicine is the way of the future. And of course, eventually, some kind of cost benefit analyses in the public health system will lead us to decide that actually is the best way, and that even the current cost would be cost effective to reduce changes in productivity of our patients or improve them more rapidly. And potentially there are insurance implications, because if somebody's been trialing and erroring 4 or 5 different medications, those are costly. The 8 or 10 months of wasted time is costly. And so from an overall, patient-centered care perspective, I do think that this personalized medicine is here to stay. It's not a flash in the pan, and it is the only way forward. And of course, the science is burgeoning, and we'll have more and more data to support this hopefully in the near future, and hopefully further reductions of costs, so that it will become. I see a future where people will show up to their doctor or their emergency department and have their entire genome sequenced and know exactly what they should or shouldn't be using, to the extent that there's evidence to support that. So I think that's perhaps all I need to say. And obviously there'll be questions at the panel at the end, so we can turn it over to Iris.
Thank you, everyone. Tim and Aaron, thank you very much for the introduction and for explaining pharmacogenomics. I would like to go a little bit more into the detail, because I'm working at SickKids, and at SickKids we're taking care of our children here in Toronto, our sick children here in Toronto. And we realized with pharmacogenomic testing that we could take better care of our children, specifically a specific group of children, our cardiology children and our children who have GI issues. And I will share some slides with you right now. So, a second. Trying to move here around. Okay, so to wrap it all together, what Tim and Aaron said, the goal of pharmacogenomics guided prescribing is to know ahead of time if someone responds to a certain medication, to reduce the side effects, and to increase efficacy. And with doing that, we would also have a better cost-benefit ratio when we prescribe medications, because some medications can be very costly. And also the trial and error, we're reducing the trial and error of medications. In addition, and this is what I realized when with our pharmacogenomics clinic, we really enhance medication compliance and increase the patient's confidence in the treatment of the disease. So what we're doing with pharmacogenomics is not only taking care of medication safety, but we also empower our patients and the parents of our patients to be part of the treatment journey. So everything which Tim and Aaron mentioned is readily available at your fingertips. So in your literature, which you're using to prescribe medication, pharmacogenomics is already a part of it. You just have to look at it. So Micromedics, Lexicomp, UpToDate, CPS, all already have pharmacogenomics information available if a medication carries pharmacogenomics information. Not every medication on the market already has pharmacogenomics implication. And the reason is that we first have to find the genetic variants which have an interaction with the medication and its enzyme pathway or the receptors it interacts with. So as Tim and Aaron mentioned, there are some barriers of clinical implementation which have to be further addressed or need to be addressed or have already been addressed. One of them, which I didn't even mention or specifically, but it is in the knowledge area, is education. We need to further educate our colleagues, physicians, nurse practitioners, pharmacists, that this testing is even available and that this is effective. Also, test-related barriers, that pharmacogenomic testing really should only be ordered through regulated clinical laboratories and not just the direct-to-consumer companies which can give you information like Aaron mentioned, which is really not helpful when you prescribe a medication, because you need to be aware that the information you're giving really has clinical validation and clinical evidence. So if you consider choosing a commercial lab as a healthcare provider for your patients, just make sure to figure out who's giving the information back. How is the data interpreted? Is it easy to interpret the data? Does it stay in the clinical realm? Because some data is not yet, pharmacogenomics data is not yet ready to be translated from research into clinical practice. And sometimes in the disclaimer, it is hidden that this data, which is given out, is not really yet available for clinical value. So here we go. What is the evidence supported? Is the evidence given supported really by current published guidelines? So our activities at SickKids, we're really trying to go towards precision child health, trying to individualize patient care as much as possible. Care was always personal, but we're really trying now at SickKids to go and come from many more directions to see how we can take care of our children also from the genomics perspective. So for right now, as of right now, pharmacogenomics at SickKids is really a pilot. And the reason why it is a pilot, because the Ministry of Health is not paying for a pharmacogenomics panel. So we cannot just open it up for every child. We have to make sure that these children fit into a specific category. And the category is if a child has been on a medication which has published guidelines, will be on a medication which has a published guidelines, or the family history shows that there were severe reactions to a medication, then we can take them in and enroll them into the study. For now, and this will change in the future, our oncology patients have been excluded from the study for several reasons, which I will not go into. So what is the workflow? How do we work? How do we work pharmacogenomics into our clinical care? It happens only through consultations. Physicians at SickKids, most of them are aware that pharmacogenomics testing is available to our children. And then my division, the clinical division of clinical pharmacology and toxicology, we have physicians and pharmacists there who will go and look at the consultation and offer pharmacogenomic testing if it is available for the child, if the child is eligible. And then we take a swab and we send the testing out to the DNA labs, who helps us, gives us a report back, and then we give it back to our patients. Also, the part of pharmacogenomics, the part of the pharmacogenomic testing, the report, is also available in the electronic health record. And that is a very important part, because thinking of it, you put so much effort into it, you test the person, you give a consultation, you talk to the physician, but 5 years down the road, everyone forgot that pharmacogenomic testing was available, because children usually, our children at SickKids usually can come back, and it is available in the electronic health record. The disadvantage is here that you have a report, and as a parent or as a patient, you are responsible that when you switch care to somewhere else to make sure that the pharmacogenomic testing, I call this the booklet, because we're talking about an 11, 12, 13-page report, that the booklet is carried with you when you go to a new healthcare provider or to the pharmacy. So what makes pharmacogenomics different in pediatrics? Because we cannot just, we need to understand that children work different, that the body of a child is different than of an adult. And there's some other things which have to be considered in pediatrics, and pharmacogenomics is just a part of it. But medication administration in children plays it plays a role how old the child is, from neonate to the adolescent. And also a big consideration is when we talk about the enzyme activity of a person, that when you're born, your enzyme activity is a little bit different than when you're an adult. And we also put this into consideration when we test for children. And usually testing for children should not happen before they are at least 4 or 5 months old. And then really the whole enzymatic effect of what we see in the report is really helpful very often after a full year has passed. So these are the drug gene combinations which we are testing through the DNA labs. As you can see, a lot of them are psychiatric medications or medications used in pain. I will not go, I will just wanted to show you the slides that we're talking here over 60 medications. Little bit newer on the list, and this is what makes pharmacogenomics so exciting, that every couple of months there are new guidelines coming up. So today we're talking about 60 medications, but in 2 or 3 or 4 years, we'll talk about 100 medication. So currently, which has been added to the list are the NSAIDs, celecoxib, flubiprofen, ibuprofen, and all of them did not have really good guidelines available up until a couple of months ago, and now we have them. So we can also help guide those medications. Neurology medications used in neurology, anti-epileptic medications, and then we have our medications which are very commonly used in our children and which we are taking care of in our cardiology department. Here are our proton pump inhibitors, which Aaron already mentioned, where enzyme activity plays a role in the metabolism of the medication. And I will give an example very soon about what we've seen in at SickKids. And there's another set of drug-gene interactions available. So, as I mentioned, one of the first pilots happened in our cardiology department, especially children who were on a transplant list. And specific medications are very commonly used on children prior to transplantation and after transplantation. And we realized that we followed 12 cardiac transplant patients, and 8 patients were cardiac transplant candidates, and 4 already have received cardiac transplantation. And we realized that in 75% of our patients, there were recommendation pharmacogenomics guidelines available for medications given to them. And we were able to adjust dosage based on those guidelines. And it really improved the care of these children because we prevented either therapeutic failure or side effects from happening to those already fragile children. We're talking about medications such as warfarin, tacrolimus, clopidogrel, the Plavix, ondansetron, and many more. Also, another project was to see in children who are placed on proton pump inhibitors and had more or less a little bit of partial therapeutic failure or complete therapeutic failure. When we looked into those children and we tested them, we realized that out of 42 children tested for therapeutic failure on PPIs, 32 patients were considered either fast metabolizers or ultra fast metabolizers. So what does it mean to be a fast metabolizer or an ultra fast metabolizer? It means that you're breaking down the medication much, much quicker than the average population. So when you assume that you give a medication like normal dosing to those children and it hits the bloodstream and it is taken out of your body, and hits the bloodstream, and before it even can show its effect, it's already taken out of the bloodstream, that you experience therapeutic failure. So either you switch to another medication, out of those proton pump inhibitor groups which are not influenced by this specific enzyme called CYP2C19, or you have to up the dose by 50 to 100% or even more to experience the same success than normal metabolizers or patients who have less than a normal metabolizer status, like poor metabolizers. So I want to shortly, very, very shortly address pharmacogenomic testing in psychiatry. So we also looked at those children, our mental health children who have to go to our psychiatrist for their mental health. And as we know, our times currently are very challenging, and there's really an explosion of using mental health psychiatrists, psychologists, care for the population. And I just want to be aware that there are a lot of companies out there who offer you pharmacogenomic testing specifically for psychiatry, for psychiatric medications, because this is such a booming place. And what I just want to be aware of that, again, as Aaron mentioned in the beginning, and I have mentioned in the beginning, there are some companies who offer you algorithms, information, which has not yet been translated from research into clinical practice. And the FDA even advised caution against these reports where the level of evidence is quite poor. However, and now I want to emphasize, however, when you look at psychiatric medications, there are two parts of pharmacogenomics which plays a role in psychiatric medications. We're talking about the metabolism, the activation or the breaking down of the medication, and then we're talking about where we have lack of evidence or lack of knowledge, the pharmacodynamics, meaning the activity of how the medication interacts with receptors, for example, in the brain. There we are not very good at, but we are very, very good at finding out if there isn't enough medication in your blood level in order to show its effect. And there we're talking about metabolism genes such as CYP2C19, CYP2D6, where we know already, where we have guidelines available that if you are a poor metabolizer or if you are an ultra rapid metabolizer and you belong to those fringes of this bell curve, that there should be alternative given to you. Either you experience a lot of side effects or you have to lower the dose, or you are a rapid or ultra rapid metabolizer where you just break it down much quicker and it is not really helpful to you. So I just want to emphasize that I am a strong believer in pharmacogenomic testing, and as we see firsthand that it really influences medication therapy. And it is another, we just have to look at pharmacogenomics as another layer of medication safety, just looking from the genetic lens. However, it is just another piece of the puzzle because it's still, we have still to look at other factors such as concomitant disease, medications, environmental factors, disease process, organ function, and many more, which plays a role in medication administration. And again, just a piece of the puzzle. I like this slide, therefore I showed it. And I thank you for listening.
Thank you, Iris. Thank you, Tim. Thank you, Aaron. We have our first question. I think Iris is probably the best one to answer. How does pharmacology testing address meds that may be used for multiple purposes, such as antidepressants for pain or depression? Iris, are you able to come back and answer?
So the question, please repeat the question. What was the question? Multiple medications used for antidepressants?
How does pharmacogenomic testing address meds that may be used for multiple purposes, such as antidepressants for pain or depression?
Okay, I understand. That's a very good question. Thank you for that question. So there are guidelines available which address exactly that part of it. If you are taking, let me say, you're taking an antidepressant for pain, we're talking here about tricyclic antidepressants. When you take a low dose of a tricyclic antidepressant, most likely pharmacogenomics will not play such a big role. However, if you up the dose, when you go to normal dosing, like for antidepressant, to prevent and to help with depression, then you go over the higher dose, then pharmacogenomics will play a much bigger role in that. So there are, the guidelines will address exactly this question.
Okay, one next question again for you, Iris. Is there currently a role for pharmacogenomics in oncology patients? I know you mentioned it briefly earlier. Are there guidelines for chemotherapy doses or other targeted oncology medication based on different metabolizers?
Also an excellent questions. Really, these are excellent questions. So oncology was one of the fields which are at the forefront of pharmacogenomics. They really pushed pharmacogenomics into the clinical practice. But we have to compare, we have to make sure that when we talk about oncology patients and about chemotherapies, that there are changes in the tumor, pharmacogenomics changes in the tumor or in the cancer, and then we have the germline pharmacogenomics. So the genetic variants, changes in our genetic variants, which we are born with. So there are two different arms of pharmacogenomics. And we excluded pharmacogenomics for oncology patients for several reasons. One of the reasons is that the funding is, if we had in the beginning include already oncology patients, they would have already eaten up the whole funding, because all of our children, oncology patients, would have liked this pharmacogenomic testing. This changes now. We will now have pharmacogenomic testing available. Germline, meaning the changes in our genetic makeup, which we are born with, not the changes in our tumor, which happened when we developed the cancer. So the changes that happened during cancer treatment in the genetic variants in our cancer, this is already playing a huge role in medication administration on a daily basis and for our oncology patients. And medications are adjusted based on those tumor-specific markers. And soon enough will help the supportive medications, which our children are taking in for chemotherapy supportive medications, will help them with the guidelines available with the germline pharmacogenomic testing.
I might add in though, there's some very specific and commonly used chemotherapies or medications anyway that change hormone production, especially in women with breast cancer. And the aromatase inhibitors like tamoxifen, for example, do have some particular pharmacogenomic potential. And so I think because breast cancer is so common and the use of the aromatase inhibitors is so common, that the pharmacogenomics around that is actually quite important, but not as commonly used perhaps as they could be.
Tim, I'm gonna give you one more question while you're here. What are ways you suggest we can increase physician readiness to use pharmacogenetic testing?
Well, Iris briefly touched on it, that it's an education aspect. Most practicing physicians have 5 or 6 minutes with a patient, and they're routinely prescribing 50 medications or more a day, and they likely are not aware that a substantial percentage of those medications would have some pharmacogenomic implication. nor are they aware how to get the testing done. And sadly, because it's not something they can tick off on a standard OHIP requisition, it would require extra time to explain to a patient why it's important and useful. When you take that time, most patients are agreeable. And again, because the cost has come down quite dramatically, you don't necessarily need to be a affluent executive to access this testing. So I think the uptake amongst patients would be higher if we were discussing it with them, but most doctors are not comfortable yet because they don't have the education to know, A, that it's useful, or B, that patients would like it. I think the big kind of sea change will come when the cost benefit analysis of these has finally crossed the desk of ministries of health, and they say, yeah, we're going to save actually a lot of money overall in our health system if we spend this up front and do more genomics. And I'm not sure when OHIP is likely to embrace this. Hopefully it's relatively soon, but it's been, as I say, at least 15 years that these tests have been available, and they haven't crossed the radar yet. So let's cross our fingers it's coming.
Do you think that pharmacogenetics will have an impact on or guide the future development of novel drugs?
I can answer that.
Agris, take that one.
Yes, it's already happening. So entities like Health Canada and FDA advise, more than advise, they expect you that if the development throughout the development of a medication, if there are variants, genetic variants involved in that it needs to be addressed. Absolutely, yes. And also the development of medication based on pharmacogenomic information is already happening.
Next question. Is this used for all drug types, such as biologics, immune suppressants?
That is a very good question. There are some biologics where pharmacogenomic data could influence medication therapy. We're not there yet to translate it from research into clinical practice, but this is upcoming.
Thank you. With cancer, wouldn't it make more sense to do both genetic tests from birth and changes in tumor? Isn't this the role of epigenetic coaching to achieve and sustain best outcomes in cancer treatment?
The short answer is absolutely yes. Yes.
Let me see if we have anybody else. I'm going to leave this one to Aaron. How's the patient's data protected? I anticipate a lot of questions about how will you keep my DNA from the government? Sounds ridiculous, but it has happened already.
Yeah, that's another great question, and that is a big concern amongst a lot of people. And anytime you read a news article about genetic testing, the comments are all about the evil insurance companies and governments trying to control people based on their genetics, or make decisions based on genetics. So, first of all, as a requirement, companies have to be HIPAA compliant with their information. So it's stored in a very secure way. And there's a short answer, but there's also now laws, both in Canada and in the US now, that are supposed to prevent discrimination based on genetics. So employers or insurance companies are not allowed to even access that information. And there's actually big penalties if they do. So that's a great question.
What are your thoughts on participating in studies on funding innovations for continuing medical education on the role of genetics in population and prevention health management?
Yeah, I can talk to that. So yeah, for sure. I mean, I think it's obviously very important, as both Iris and Tim mentioned, that it's the education is a huge barrier. So the more we can get out there, the better. I think it's very important. Thank you.
Do you think there will be a pharmacogenomics data for nutraceuticals and herbal supplements soon?
Tim, do you want to talk, or do you want me to?
So there's a bit of a challenge around some of the natural health products that are used routinely, in that they're often not pure compounds. They haven't been purified down to a specific ingredient. Take, for example, St. John's wort, which has been studied on its own as a useful medication for antidepressant, and in fact has efficacy rates that are approaching those of prescription antidepressants. However, there are, in an herbal like that, there are potentially hundreds of compounds, and they may all be metabolized differently. So I think there's a bit of a bigger challenge there in terms of producing evidence that for example, is going to work better in one person or another. But Aaron, you can perhaps speak specifically to the genetics of that.
Yeah, well, I just, the only thing I would add is that just because someone has a potential nutrient deficiency does not necessarily mean, or sorry, just because they have a genetic risk of a nutrient deficiency does not necessarily mean that they have a nutrient deficiency. So just a great example is iron. I have a risk of iron deficiency, but because of my diet, I do not have symptoms of iron deficiency. And if I was to run out and get an iron supplement, that could be very dangerous for me, because there's something called iron overload, which can be harmful. So yeah, I think with nutraceuticals and herbal supplements, I think you really have to understand not just the genetics, but also the diet, the goals, the symptoms, and that sort of thing.
So I will just say that 23andMe were shut down by the FDA because they went direct to consumer with a report that was fairly complex and quite medical. And ultimately, I think that the way forward here is not to cut out the medical profession, but to Aaron's point, it's not just what your genomics tells us, it's what epigenetic influences you're having on those genes and what your lifestyle is and what you're actually doing, and then family history. And so it really has to be contextualized with any individual patient about their past history and the current health history to put a lot of those additional genomics testing, not just pharmacogenomics, but all the panels of genomics that we have. And to his point that there are, for example, very common polymorphisms that lead folks to have low vitamin D level. And vitamin D is now we know critically important for surviving COVID, for example. Mm-hmm. So one of the public health misses here, I think, is that we haven't emphasized the importance of getting an optimal vitamin D level. Well, we can predict from the genomics testing that somebody is likely to have a low D, but if they spend their entire winter in Florida, they probably won't have that problem. Or if they're supplementing with 10,000 units a day, they won't have that problem. So not just the genomics, we need to do a blood test and we need to speak to the patient and see what they're doing before we can contextualize that.
Absolutely.
And I want to emphasize this also with pharmacogenomics. If you have the report available and the report is really going into detail, it cannot be taken out of the context with drug-drug interaction, drug-food interaction, and drug-disease interaction. And also if sometimes a medication is on the red column, it doesn't mean do not take it completely. It says alternative medications should be available. Think about alternative medications. Sometimes there is not an alternative, but then a healthcare provider or someone who understands pharmacogenomics is very helpful in being able to dose it in a safe manner for this patient. So it is very important to have the healthcare provider, a pharmacist, a physician who understands, nurse practitioner who understands pharmacogenomics information or genomics information to guide the patient for the right dosing, or other healthcare providers.
Thank you, Iris. Thank you, Tim. Thank you, Aaron. And thank you everybody that attended. It was a great event, very informative. And if anybody has any questions, they can email either Aaron at dnalabs.ca, or myself, Moni at dnalabs.ca, and we'll get back to you with an answer. Thank you very much and have a great day, everybody, and stay safe.
Thanks, everyone.
Thanks.